Good morning. This is week 4, Data Integrity. My name is Charles W. Bill Marshall, and that's my telephone number and email address if you want to get in contact with me. We're working on CIT253, which is a 3-credit-hour course, DataDriven Web Pages. And as always, Blackboard's the official site for assignments and to turn in assignments, but I have another website if you want to see any of this supporting information. Alright, so we're going to talk about two tables, order detail and item location. Order detail has the order number, the line number, the item code, the order quantity, committed quantity, and back order quantity. And as we go through, you'll figure out why we have 3 quantities. But item location only has an item code and a rack on count. So we have a simple world where we only have inventory stored one place. If we know the item, we know how much rack on hand count we have. Alright, so what's the process to check stock and commit stock? Well, we're going to have to go to read order detail for the item code and item quantity. Then we're going to have to read the current rack on hand from the item. Then we're going to have to make a decision. If the current rack on hand is greater than or equal to the order quantity, well then it's easy. We just say the committed quantity equals the order quantity and the back ordered quantity equals 0. But if it's less than, we're going to have to say the committed quantity equals the current rack on hand and the back ordered quantity equals the order quantity minus the current rack on hand. But what about the next fellow who comes through, or next lady? Well, we're going to need to, no matter what, say that the current rack on hand back in this table is equal to the current rack on hand minus the committed quantity. Alright, so that's great for one user, but when we have 2 users, if we do things quickly, I guess it'll still work because the first user came through and we were at the speed of light, miraculously able to get back and update our tables so that when the second user comes in, they do the same thing and life is good. But what happens if time passes for whatever reason? The phone rings, somebody has trouble, and you get into a situation like this where the first user comes in, we read their data, but before we make the updates, a second user comes in. Well, they saw that there was 10 to start with, and this person wanted 5. Well, this user wants 9. In this situation, when they read, there's still 10 on the shelf. I mean, they still want 9 and there's still 10 on the shelf. They make their decision. This person says, well, I put back, there's still 5 there only. This person comes in and says, well, no, I took 9 and there's 1 there. So we are in deep trouble because we've overcommitted. Alright, so the world has come up with a thing called the database transaction, which is a unit of work that's performed on a data management or similar system, and against the database and treated as coherent and reliable way for independent of other transactions. So until that transaction happens, nothing happens. Transaction is a database environment for 2 main purposes: to provide reliable units of work that allow the correct recovery from failures, and to keep database consistent even in cases of system failure when the execution stops or only completes partially. Many operations upon the database remain uncompleted and an unclear status. So we're talking about what happens when you have a system failure. The power goes off, the network goes down, and so forth. To provide isolation between programs accessing the database concurrently, if this isolation is not provided, the program's outcome is possibly erroneous, as we just demonstrated. Okay. So, in a database management system, it's a single unit of work, sometimes made on multiple operations. In our case, we were going to do a read, 2 reads, and an update. Any logical calculation done in a consistent node of a database is known as a transaction. One example is a transfer from one bank account to another. To complete the transaction requires subtraction of the amount from the transferred one and adding to the same amount to the other. Alright. A database transaction is, by definition, it must be atomic. It must be either complete entirely or have no effect whatsoever. It must be consistent. It must conform to existing constraints of the database. Say that you have a rule that says you can't have a balance below 0. Well, the transaction ought to, in fact, if it's getting ready to violate that constraint, it ought to abort and have no effect. It needs to be isolated. It must not affect other transactions until it completes. It must be durable. It's got to be written in a persistent storage. Database practitioners often refer to these properties as ACID, and you will hear that term again. And if you have more questions, as always, you can go to Wikipedia to that address, or quite frankly, when you have a question about any of this stuff, it's all very present on Google. And if you don't like this presentation, there's 1,000 more that you may like better out there. Okay, so in our world, that order entry transaction we would have, before we got to here, we would begin work. And then we would read, and we would read the other table, and we would make our decision. We'd do our calculations. We'd go back and update the table 2. And then we would commit work, which means, okay, we want all these to happen as one transaction. When we do a begin work means that each row in that update, delete, insert, or merge statement affects during the transaction is locked and remains locked throughout the transaction. The transaction logs each row of that action requests. Okay, and that can lead to running out of locks. A transaction that contains many such statements or contains statements that affect many rows can exceed the limit of your operating system or the database server imposes on the number of simultaneous locks. The other thing we talked about was a commit work. Commit work statement informs the database server that you've reached the end of the series of statements that must succeed as a single unit. The database server takes the required steps all at once to make sure that all modifications to the transactions are completely correct and saved to disk. Commit work. Rollback work. So you have to have the ability that if something happens that you don't like, and it's something you decide programmatically, if you get to this point in the logic tree, you want to roll back. A rollback work statement cancels all or part of the current transaction intentionally, undoing any changes that occurred since the beginning of the transaction or since the begin work. Okay. We have the ability to do table level locking. With table level, when we begin work, this whole table, order DEET, is locked. And then the ILN table is locked. And nobody can get into them until we get over here to commit. So it's not just one row, we've locked the whole table. The advantage is that we don't need many locks. The disadvantage is we've locked the whole table. The other option is row level locking. With row level locking, you begin work and lock the row that this item code is on, and we lock the ILN of this table for that item code, and then we go over here and write stuff back to them and commit work. But during that whole time, we've only locked the rows for that item code and that item code for that row of the order, and for that item code in the item master. But you can run out of locks with row level if you're not careful. So you need a record for each thing, row or table, that you've locked. When the database is created, an area to store locks is allocated. The size needed, you need to anticipate the size based on the type of transaction. Is it going to be an OLTP, online transaction processing, an OLAP, an online analytical processing, or an ETL, an extraction, transformation, and loading? And these are critical terms, so let's look at each one. OLTP, or online transaction processing. It's a system that captures and maintains transaction data in a database. Each transaction involves an individual database records and made up of multiple fields or rows. And examples would be a banking, where you are logging banking transactions, or a credit card activity, a retail checkout scanning at a grocery store or at a restaurant. And probably the classic today is e-commerce website, where somebody like Amazon is dealing millions of transactions a day, and they need to know whether something's in stock or out of stock in real time. That was Amazon when I set her off just recently. Okay, the next type of transaction is OLAP, online analytical processing. It applies to complex queries to large amounts of historical data, aggregating from OLTP databases and other sources for data mining, analytics, and business intelligence projects. And so you reach a point where you don't want to risk your OLTP activity, or you just can't, the system doesn't have enough cycles in it to support OLTP and OLAP. An OLAP, the emphasis is on response time for the complex queries. Each query involves one or more columns of data aggregated across many rows. And so we're talking about the sales team comes in and they want to look at how many they've sold by state, because they're getting ready to go to a meeting where they're going to have everybody that sells in that state represented. Or you've got a salesman that's getting ready to go to that state, and he wants to know when he's talking to the customers who's up and who's down. Or you have the finance man who's trying to understand what his cash requirements are going to look like. Or you have somebody in purchasing that's trying to understand what the vendor delivery has been for a vendor he's expecting to call on him for the sales call tomorrow, and he wants to know whether he should compliment him or chastise him. The examples include year-end financial performance, month-end financial marketing lead generation trends like we talked about. OLT databases and data warehouses give analytical and decision makers the ability to use custom reporting tools and turn data into information. So you make a lot of information with OLTP, and you hope that OLAP will help you know what to do next to keep the transactions coming. A query failure in OLAP does not interrupt or delay transaction processing for customers, but it can delay and impact the accuracy of business intelligence insights. And I will tell you that the CEO or the general manager or the sales management who come in want their reports the first thing in the morning. And you would think the world was going to end if the reports aren't there. And in fact, it deeply impacts their ability to make real-time decisions to run the business. I'll also tell you that I worked at one Fortune 500 company for sales that had a decision with OLAP reports that once a year they would not run every report. And their premises was that they didn't run the report, and if nobody noticed, they never ran it again. Because you can get a lot of reports that one manager uses and take a lot of cycles, and when he promotes or leaves the company or goes to another division or whatever, the system's still driving through all this report, but nobody's looking at it. And the days of mainframes and printers are dying, and so it's more that you're using something like Click or used to be Crystal Reports until they were bought by SAP, that people can generate reports on the fly. You have to be sure that those reports don't take down your ability to respond to customers in real time, though. Okay, and the last thing we talked about was ETL, or extraction, transformation, and loading. And that's the force that joins OLTP to OLAP. So how do you get all that data that you had in your online transaction processing to your analytical engine? It's a process where data is extracted from data sources that are not optimized for analytics. It's moved to a central host, which is, we hope, the extraction steps in the process might differ from one OELT tool to the next, but the end result's the same. At the most basic, you extract data, you transform data, and you load data into another system. While abbreviation implies a neat three-step process, extraction, transformation, and load aren't. The transportation of data, the overlap between each of these stages, you may have ways to do them, and it depends on how many different entities you've got. If you're in the SAD world where there is a purchasing system and a different one for an inventory system and a different one for a sales system, or even if you get to the place where it's a division, the corporate division is 20 companies merged together and none of them count anything the same, you have to come up with a way to move all those different units of measure and ways of speaking back into a common world. Spent a year doing that. And new technologies continually change that flow. Okay. Another thing you got to worry about, the system is hung. Somebody says to you, the system's hung due to a long transaction. Okay. The system logs each step of a transaction we talked about. To protect these logs, it has to protect these logs until it gets to a commit work or rollback work. If all the log space is, quote, in use, then you have hung the database. And that doesn't mean just you're hung. It means that all programs that need to log their transactions are hung. Care must be used to correct this situation without corrupting data. And it can be done, but it has to be done carefully. And that's a good time to read the manual to make sure you know what you're getting ready to do before you push the button. All right. Another problem you can have is a deadlock, also called the fatal embrace or the deadly embrace. And it's another crippling condition. It occurs when two or more programs are each waiting for the other to complete. or even just produce data value before they proceeding. In our example, it would be somebody can't read data until the item catalog is available, but there's another machine that's got the item catalog that can't do anything until they can read the order detail line or some such. The programs act overly congenially gophers in some Looney Tunes cartoon, and says, "Oh, please, you first." And the other one says, "No, I insist, you first." And nothing goes anywhere. So as you design your storage and your commitments and your begin work and end work, you have to consciously think that you don't get into one of these situations. And the object of the game is to keep the distance between begin work and commit work very short. In the order entry programs I wrote for Stober, you would begin work and commit work several places through processing each line of the order so that you didn't get into a deadlock. All right, and another friend that you need to keep in mind is a dirty read, which is you say to the system, this program is only reading, it's never going to write, and I want the best data that you've got right now, but I'm doing a dirty read so that if it changes, I can live with that. It does not observe lock rules. It will read locked data. It must not need to write data to that table because there's no way you can keep data consistency. Sales reports are classic examples of dirty read. You want to know, you want to tell the salesman what is as of right now, and he knows that 5 minutes later you may have had 100 people place orders, but as of right now it was the best you knew. Also consider the real world. So we've talked about all these ways to lock data, but our process said that a customer ordered data, they went out and checked stock, and they wouldn't change stock, and we committed work. But what happens when somebody cancels an order and we've already taken the stock for that order? How does the inventory get released? Well, another option would be to say that at any given time we're going to check stock, but we're not going to change the stock level until we actually pick it or until we actually ship it. And in that case, then if you cancel the order, all the work goes away. So keep total inventory by item code and warehouse. Track the status of order lines: new, ordered, pick, ship, invoice, and post. And you may change the location in the warehouse at the pick stage, but don't change the inventory in the warehouse until you get to the post stage, or maybe the invoice stage. And you need to think through that, and it's more than the scope of this lesson, but you need to really think about the real world when people change their mind or increase the order or whatever. Okay. So as you track the status of order lines, you not only have to worry about begin work, commit works, but you need to think through the process of, if somebody, what have I actually done at the point where I mark it to ORD stage? Do I want to change the inventory in the warehouse at that point, or do I want to have some way to calculate the available inventory but not physically change the inventory? When I get to the ship stage, do I want to change the inventory in the warehouse? When I get to the invoice stage and I've affected the cost of goods and affected the accounts receivable, do I want to change the inventory? Do I want to do it when I get to the PST? Where you actually do it is past the level of this discussion, but it is a thought process you ought to have, because people will cancel orders and people will change orders, and so begin work, commit work cannot help you there. you have to have a process that thinks through how you're going to handle that. So I'm advocating only reduce the warehouse inventory when the order is posted or as completed. But that may not be right for you. Okay, and if you want to see other videos on ACID transactions, then this is a good link, but like I say, Google will take you to many good links. I hope that's given you some thought about data integrity, and if you have questions, please contact me. Thank you.